What if your computer changed every time you looked at it? You might think that sounds bizarre, but that's what happens with quantum computers. The key difference is how measurement works in classical versus quantum physics. Consider measuring the temperature of the air with a liquid-filled thermometer. As air molecules bump into the glass around the liquid in the thermometer, they add energy to the liquid and make it expand. The hotter the air is, the more energy the air molecules transfer to the liquid, and the more it expands. Except for the very tiny amount of energy transferred from the air to the liquid, the energy of the air doesn't change. Measuring a classical system doesn't usually change that system in a noticeable way. But the situation is quite different for quantum computers and other quantum systems. Just as how air molecules have energy, quantum systems like atoms also have energy. For example, an atom with an electron far away from the nucleus has more energy than the same atom with the electron close to the nucleus. But how do we measure the energy of a single atom? It's a much smaller and more delicate system than air and thermometers, so the answer is more subtle. One way is to shine a laser on the atom. The measurement involves probing that atom's electrons with photons or small packets of light. The laser light interacts with the electron, and the energy of the atom determines the color we see in the light bouncing off the atom. More generally, the act of measuring a quantum system will significantly change that system, unlike classical systems. That's why if you have a quantum computer, every time you look at or measure the information, you actually change the state of that information inside the quantum computer. This is one reason why it's so hard to build quantum computers. They need to be extremely well isolated from their environments so we don't accidentally measure them when we don't want to. It's also why building quantum algorithms can be so tricky. You have to measure the qubits at just the right time to take full advantage of superposition, because as soon as you measure a qubit in superposition, it collapses into a single state. It's also a reason why quantum computers are so powerful. Before we measure them, the possibility to have superposition leads to very fast algorithms for some problems. We just need to be sure we measure at the right time.